Okay, continuing on physical chemistry, chapter 17, section 3, where I'm talking about two competing reactions and how one reactant A can go to two different products, C and D, and how one of the products can be favored kinetically and the other can be favored thermodynamically. Kinetically, thermodynamically. So this is the reaction to explain how that's possible. Let's say we have this reaction here. We have a diene, and we're going to add HBr. So on one hand, we're going to have 1,2 addition because the hydrogen is going to go here and the bromine is going to go right here. On the other hand, we're going to have 1,4 addition because the hydrogen is going to go over here and the bromine is going to go way over here. So these are isomers of each other. Now you'll notice at negative 80 degrees, you're going to have almost you're going to have 80% 1,2 addition and just 20% 1,4 addition. But at positive 40 degrees Celsius, you're going to have 20% of the 1,2 addition and then 80% of the 1,4 addition. Now, what that tells us, the 1,2 addition is kinetically favored and the 1,4 addition is thermodynamically favored. Now, how is that possible? Well, this is a diagram showing energy versus reaction coordinate. Now, this is just between the two isomers. We're leaving out the reactant here. So, you've got this intermediate product. You've got this hydrogen already added. You've got double bonds here. Well, it's kind of a double bond. There's resonance going on. So you have a partial positive over here at the 4 spot, and you have a partial positive here at the 2 spot. So this shows you the energy of this intermediate product. Now, to do anything, you've got to overcome the activation energy. For 1,2 addition, you have lower activation energy. So the 1,2 is favored kinetically, just like we said. It has a lower energy of activation. On the other hand, you'll notice its final energy is way up here. The 1,4 addition, it's got a higher hump, which means it's not favored kinetically, but it ends up with lower energy final. So that means that this is the thermodynamically favored product. Alright, continue on physical chemistry, chapter 17. Finally, we're in section 4. In section 4, we're going to learn different ways to actually determine the rate loss. Now, this has to be done experimentally. Now, we have the generic form, R equals K times the concentration of A to the alpha times the concentration of B to the beta, etc., times all the way to L to lambda, whatever, it might be different reactants in here, it could be catalyst, whatever. This is definitely something that has to be done experimentally. Now, how do we find the values, though, for alpha, beta, lambda, and, of course, most importantly, K, the rate constant? Well, one method is the half-life method. This one's easier to understand and easy to do math, but it's not always useful, not always the best. But you have rate is equal just to K that equals A to the N. If we, keep the others constant or whatever and do it like that. So, or if we just have one substance, of first order reaction of this type, or not first order, any order but of this type, only one reactant. So if N equals 1, then we know the half-life is independent of the initial concentration of A. That's easy enough. So you do an experiment and you see if the half-life is independent of concentration of A, and if it's not, then you know it's first order. On the other hand, if N is not equal to 1, we derived last section that the half-life is equal to 2 to the N minus 1 over N minus 1 times the initial concentration of A to the N minus 1 over K. So what we want to do, we're going to split this out, and then we're going to take the log of that. So we get the log of the half-life is equal to log of 2 to the N minus 1 over N minus 1K minus N minus 1 times log of A naught. Now, this may look uglier than that, but you realize now we have a straight line in slope y-intercept form. You experimentally find your half-lives, and you graph the half-lives versus the log here. So you have the intercept. This is just some constant, but you notice you got your K in it, so that might help. And then you've got your different concentrations of A. So you just do the experiment multiple times with different initial concentrations of A or whatever. And then N minus 1 is the slope. Okay, continuing on physical chemistry, chapter 17, section 4, we're doing the half-life method of determining rate equations. So So we're graphing the logarithm of the half-life here, the time for each half-life, and then we're against the logarithm of the initial concentration of A. So if we do that, we showed before how the slope is going to be equal to minus n minus 1, which is equal to 1 minus n, as long as n is not equal to 1. So what you do is you collect all these data points. Like you start out with an initial concentration A naught prime, and you wait for it to hit 1/2 that, and that'll give you 1 half-life. And then you start another initial concentration A naught double prime, you wait for half of that, that'll give you another time for the half-life. And then you start another initial concentration A of triple prime, and then just wait for 1/2 of that, and that'll be your time 1/2, etc. Continue on physical chemistry, chapter 17, section 4. So we're continuing, we got the fractional-life method, which is kind of like the half-life method, so we're not numbering it separately. So we're going to define the time of alpha is the time required for A naught to drop to alpha times A naught. So like when we did T 1/2, the half-life, alpha is 1/2. And obviously alpha has to be between 0 and 1. So if R is equal to K times the initial concentration of A to the N, you take the log of, just like we did before, but instead of for T 1/2 is T alpha. So we get the log of T alpha equals log of alpha to the 1 minus n minus 1 over n minus 1 times K minus n minus 1 times log of A naught, n naught equal to 1. So you can graph it and determine the order just like we did for the half-life. Except alpha, you can also say it's the amount of substance left divided by the initial substance. So you could say it's a fraction too. So you take this T alpha, if n is equal to 1, it's just minus the natural log of alpha divided by K. For an actual experiment, alpha, you could, instead of going with 1/2 of the half-life, it's sometimes a lot easier just go to 0.75. Now in physical chemistry, chapter 17, section 4, we're talking about different ways to determine the rate laws. The second one is the Powell-plot. So let's say we're starting with the same reaction. R is equal to K times the concentration of A to the N, and we need to find out what N and K are. Now we're going to say alpha is a dimensionless parameter. It's actually the same way we defined it on the previous slide. Alpha is the concentration of A divided by the initial concentration of A. And we also have phi. Phi is going to be A times the initial concentration of A to the n minus 1 times T. Now if you have, for n equal to 1, we have phi is equal to KT, and the natural log of alpha is equal to minus phi. Now phi is also dimensionless here. So now we have this ratio, A over A naught to the 1 minus n is equal to 1 plus A naught to the n minus 1 times n minus 1 times KT. And this is for n is not equal to 1. So we get alpha to the 1 minus n, because this is equal to alpha, minus 1, because we moved it over here, equals n minus 1 times phi. And that's for n is not equal to 1. Now, the natural log of alpha is equal to minus kt is equal to minus phi by transitivity of equality for n equals 1. Okay, continuing on physical chemistry, second way of determining rate laws is Powell method. So we have this alpha here. It's A over A naught to the 1 minus n equals 1 plus A naught to the n minus 1 times n minus 1 kt. This is only true for n is not equal to 1. And we have alpha to the 1 minus n minus 1 is equal to n minus 1 phi, where n is not equal to 1. So taking the natural log here, we get a natural log of A over A naught equal to minus kt. So now we get a natural log of alpha equals phi. Now, n, that's for n equals 1. And then phi is equal to A naught times t, and that's equal to kt. So we get phi is equal to k times A naught to the n minus 1 times t. So we get the log, taking the log of this obviously, log of phi is equal to minus log of k times A naught to the n minus 1. So it's the natural log of this whole quantity actually. Probably should put parentheses there. and then plus log of t. And then we have log of phi minus log of t, moving that over, equals log of k. It's this whole product here, log. So then we get log of, so we know this term here is constant, because this is a constant, this is a constant. So this whole thing is constant. Therefore, this difference over here must also be constant. Okay, continue on physical chemistry, chapter 17, section 4. Now we're doing the initial rate method. So we have R naught, that's initial rate, equals K, the rate constant, times A naught to the alpha, times B naught to the beta, times C naught to the lambda. And we're talking about a reaction where we go A, B, and C to products, one or more products. Now we're going to do multiple experiments. We're going to have number for experiment number. So we're going to have ratio the rate of experiment number 1 divided by the rate of experiment number 2. Now the first thing we're going to do, we're going to have the A naught in experiment 1 different from the A naught experiment 2, but all the other initial concentrations we're going to hold constant. So if we divide the rate of experiment 1 divided by the rate of experiment 2, the constants are going to cancel out, and all those other substances we get constant are going to cancel out. So we're going to end up with just the A naught to the alpha in experiment 1 divided by A naught to the alpha in experiment 2. So that's what we're writing here, even though it's kind of funny notation. It's the ratio of A naughts to this lambda. This is the lambda, or probably should have called it alpha, but it could be depending on whatever. So, like let's say we got 1.35 for the difference in rates, even though we use 1.65 for a difference in initial concentrations. All we have to do is solve for n. So we're going to get, well, now we change it back to alpha. But anyway, so we get alpha is equal to natural log of 1.35 divided by natural log of 0.65. So for this experiment, the order with respect to A, substance A, is 0.6. Continuing on physical chemistry, chapter 17, section 4. The last method we're going to talk about is the isolation method. So let's say we have a reaction A and B and C going to products, one or more products. So we're going to say the rate is equal to K prime times A naught to the alpha times B naught to the beta times C naught to the lambda. Now what we're going to do is we're going to hold all but one constant. No, we're going to have one of them much less than the others. We're going to make one of them the limiting reagent. So we're going to make A the limiting reagent. So we're going to say the initial A, the concentration of A is much less than the initial concentration of B. And the initial concentration of A is much less than the initial concentration of C. So we have R is equal to K times alpha to the naught. So this new constant K here is equal to all these other stuff we kept constant up here. K prime, B naught beta, C naught alpha. And all those are constant. So what we did was we made this a pseudo-order reaction. This is going to be an alpha order reaction. So then we just used the half-life method or the fractional-life method or Powell method to find the order of the reaction, and that'll give us alpha. So then you make B the limiting reagent. So you make B naught much less than C naught and B naught much less than A naught, and then you do the experiment and you find beta. And likewise, you make C the limiting reagent, so you make C naught much less than B naught and C naught much less than A naught, and then you can find the order with respect to lambda. Okay, continue on physical chemistry, chapter 17. Now we're in section 5. Section 5, we're talking about rate laws and equilibrium constants for elementary reactions. Now, an elementary reaction or elementary step means it can't be broken down into smaller steps. This will become clear as I show you some examples here. Now, the molecularity of a reaction, the concept only applies to an elementary reaction or an elementary step. And it's the number of molecules involved in those elementary step. Namely the number of reactants. But again, you'll see what that means when we get here. So for example, let's say we have just A going into a product. This is unimolecular. So an example would be isomerization. You have some molecule and it cis and it turns into a trans molecule. That would be could be a unimolecular reaction. If you have 2A, like A plus A going to products, that would be bimolecular. Or if you have A plus B going to products, that would still be bimolecular. And then when you have three molecules at the same time, or three molecules in the elementary step, it could be three of the same type, so it would be 3A going to products, that would be termolecular. Or you could have two of one and a different one, that would be termolecular still. Or you could have three different molecules going to products, and that would be still called termolecular. Termolecular is the same thing as trimolecular. And this is very rare because if you think about it, it's relatively rare to have three molecules in the exact same spot at the exact same time. It's much more likely that you'll just have a pair collide. Okay, continuing on physical chemistry, chapter 17, section 5. For an elementary reaction, we're going to say we have A and B going to products, but this time we're going to leave in the stoichiometric coefficient. So we have A of A and B of B going to products. Now we're going to write then, we can say that the rate is equal to K times the concentration of A to the 8th power. That's a lowercase a, not a number 8. And then concentration of B to the bth power. Now remember, we can only do this if it's an elementary reaction. An elementary reaction is the only time that we can take the stoichiometric coefficients in the rate law and then use them in the exponent from the reaction to the rate law. So, like I said, don't be tempted to do that with a multi-step reaction, a regular reaction, because you really do have to come up with a way to determine the rate law. So any bimolecular reaction then is going to be second order, but not all second order reactions are bimolecular. Because if you have a second order reaction, it could have multiple steps, and those steps could be all sorts of different orders. So what is the relationship between Kc, which is the equilibrium constant, and then Kf, which is the rate constant for the forward reaction, and also Kr, the rate constant for the reverse reaction for an elementary reaction? That's what we want to figure out. Continuing on physical chemistry, chapter 17, section 5. So now let's say we have this reaction, A of A plus B of B, in equilibrium with C is C and D and D. So we have two reaction coefficient or rate constants, one for the forward reaction, one for the reverse reaction. So we're saying this is a reversible elementary reaction. So the rate forward is going to be equal to your rate constant for the forward reaction times A to the A times B to the B, because A and B are the reactants. And this is only because it's an elementary reaction, and this is for the forward reaction. Then the rate going reverse is going to be the rate constant for the reverse reaction, and that's times C to the C times D to the D, and that's because C and D are the reactants for the reverse reaction. And again, this would only be true for an elementary reaction, and this is for the reverse reaction. And remember, elementary means it happens in one step. If you have a reaction that happens in multiple steps, it's not a elementary reaction, so you can't use this at all. So at equilibrium, remember, the rate forward is going to be equal to the rate reverse because the overall concentrations of the substances are not changing. So we just set those two equal to each other. We have the rate constant for the forward reaction times the reactants is equal to the rate constant for the reverse reaction times the products, because the products are the reactants for the reverse reaction. Now, solving for the constants then, we get Kf over, oops, that should be K. So we get the constant for the forward reaction divided by the constant for the reverse reaction. Let me fix that real quick. And that's equal to the concentrate of the products over the reactants. And we also know that is equal to the equilibrium constant Kc. So we know that the equilibrium constant Kc is equal to the rate for the forward reaction divided by the rate for the reverse reaction. But only if you're talking about an elementary reaction. So if the forward reaction has a higher constant than the reverse reaction, then you're going to get the equilibrium constant much greater than 1, and that means equilibrium is favoring the products. If you have a rate constant much less for the forward reaction than the reverse reaction, that means your equilibrium constant is going to be less than 1, and then your equilibrium is going to favor the reactants. This is Physical Chemistry, Chapter 17, Section 6. Now we're going to be talking about reaction mechanisms. A mechanism is a very hypothetical situation based on evidence that explains exactly how a reaction takes place. Now, the first type we're going to do, or reaction mechanism, a way of finding out the mechanism, I should say, is the rate determining step, or RDS approximation. So what this is going to do is let us going to take a mechanism and then find a rate law for the overall reaction based on the mechanism for the reaction. This approach is also called the equilibrium approach. Now, let's do an example here. We have some sort of acid plus a nitrous acid plus a phenyl NH2, what was that? Aniline. And then inside a catalyst of bromide. And then remember this phe is a phenyl group, C6H5, so it's the same thing as a benzene ring basically. And then it's going to make this salt, I forgot if it's called azonium or diazonium, I'll let you look that up yourself and figure it out. Plus water, of course. Continue on physical chemistry, chapter 17, section 6. So this is our observed rate law that we got from doing actual experiments. We're going to leave the rate constant K instead of putting the actual number because there's no point in being specific. It's temperature dependent and so on anyway. So we have the constant, of course, times the concentration of the acid, just H+, times the concentration of this species, HNO2, I think that's nitrous acid, times the concentration of the Br-. So this is the proposed mechanism to try to explain this rate law. So the first step, we're going top to bottom obviously, we're going to take H+ and HNO2, and it's going to be in equilibrium with H2NO2+. And we're going to say this is a fast reaction. So notice you have two rate constants, K1 for the forward reaction, and then K-1 for the reverse reaction. Then the second step, since that's second step, we're going to have its rate constant K2. So we're going to say, okay, this species here, H2NO2+, plus Br- is going to go one way to this ONBr, which is nitrazine bromide, plus H2O. And we're going to say this is the slow step. Since the chain is only as strong as its weakest link, the slow step is what determines the overall speed. So this is going to be called our rate determining step, or RDS for short. Then we're going to take this same nitrazine bromide and add this phenyl, aniline, and we're going to go one way, so we have another rate constant, K3, to this phenyl N2+, whatever that's called, plus H2O plus the bromide. Notice we get the bromide back because it's a catalyst. Since catalyst, you always start out and end up with the same amount. If you add up all these steps, I'm not going to bother to do it for you because it's easy, any intermediates and any catalysts will cancel out, so you'll just end up with reactants on the left and reactants on the right. So in this case, it does work out. So we're saying so far the reaction is plausible. We haven't proven anything yet, but we haven't ruled anything out yet either. So also the rate determining step, it should have the same rate law as the overall reaction. Like I said, if this is the slowest step in the mechanism, then this is going to be the step that determines the rate that everything happens. So that, let's see. So what we're going to do then, to find the rate law of this reaction up here, well, to verify this basically, we're going to start with step 2 and see what we can do with that. Alright, continuing the rate determining step here. So remember from step 2 of our mechanism, this was our rate law here. H2NO2 plus Br minus, the equilibrium, or the rate constant K2, and then ONBr plus H2O. So just based on this step, we have the rate constant K2 times the concentration of each reactant, H2NO2 plus Br minus. Now that's an unfortunate turn of events because this H2NO2 plus is actually an intermediate in our overall reaction. So what we can't have an intermediate in our rate law. So what we have to do is figure out a way to substitute this out. Now remember from step 1 of this mechanism, we had H plus HNO2 in equilibrium with H2NO2 plus. So what we're going to do is use this to find concentration of this and substitute it back in up here. Now remember, equilibrium constant we showed before, that's equal to K1 over the forward rate constant divided by the reverse rate constant. In this case, K1 over K minus 1. So that's going to, and then that's also equal to the concentration over here of the H2NO2 plus divided by the concentration of the H plus and the HNO2. So just taking this part here and ignoring this, because it's redundant anyway, solving for this, we now have a concentration of H2NO2 plus is equal to the forward rate constant divided by the reverse rate constant times the concentration of H plus times the concentration of HNO2. Now, we take this whole thing and substitute it in here. So we still have that R equals K2, and then the K1 over K minus 1 times this H plus HNO2 times the bromide that we had before. Now we don't need three different constants in one reaction, that's silly. So we just combine that to say K, and we write it just like this. R equals K times H plus times HNO2 times Br minus. So this here, this is our rate law that we have deduced from the mechanism. Notice we used the rate determining step and the step before it. We did not use the fast steps after the rate determining step at all. Doesn't matter. So this is our rate law based on the proposed mechanism, and it matches the rate law that we had before that was given from experimental data. So based on that, we can still say that our mechanism is plausible. Notice we haven't proven it's true yet, but at least we haven't ruled it out yet either. Okay, we're doing reaction mechanisms and how to use them to find a rate law. We just finished the first one, rate determining step approximation. Now we're doing a different approximation. It's called the steady state approximation, also known as the stationary state approximation. Now this one's going to lead to a little bit more complicated rate law, but notice I didn't say which one's more accurate. So any intermediate, we're going to just call that capital I for now, not to be confused with iodine, obviously. But anyway, so let's assume that the concentration of the intermediate is constant. So the derivative of the concentration of the intermediate with respect to time is equal to 0. So what that means is we're not at the beginning of the reaction, we're not at the end of the reaction, we're somewhere in the middle, and because of that, we're just assuming that we have intermediates and their concentration is constant. So this won't be, whatever rate law we're going to find, it won't be good for the very beginning and end of the reaction maybe, but at least it'll be good somewhere in the middle. We'll see. Okay, so we're going to talk about the exact same mechanism we did before. So here it is, just to refresh your memory. We're going to have the H plus and HNO2 in equilibrium with H2NO2 plus. So we have forward rate constant K1, reverse rate constant K minus 1. And then we have H2NO2 plus Br minus going one way to ONBr plus H2O. So we have just one rate constant, the forward rate constant. We're calling that K2 since it's the second reaction, elementary reaction. And then we have ONBr plus this aniline, remember this is the phenyl group, going one way to this, whatever this is, phenyl N2O plus water plus Br minus. And again, this is one way, so we just have the forward rate constant K3. Now, hopefully you can tell that since we're creating this H2NO2 plus, and then using it up again, H2NO2 plus here, this is just an intermediate. And then likewise, what's the other intermediate here? Oh, this ONBr. So we're creating this ONBr in reaction 2, and then we're using it up in reaction 3. So the ONBr and the H2NO2 plus, those are both intermediates. Now remember, here we don't have to know which is the rate determining step or anything. We're just going to start at the very last reaction. So we're going to write a rate law for the very last reaction. So the rate law for that will be this K3 times the concentration of ONBr times the concentration of this aniline, I guess it's called. Okay, we're going to call this equation 1 because we're going to have to come back to it. We're going to do some substitution. You see, the problem we have here is we have a rate law based with an intermediate in it, and we can't have a rate law with an intermediate. So we need to figure out how we're going to substitute for this concentration of ONBr so we don't have an intermediate in our rate law. All right, continuing on the steady state approximation. I already mentioned before that we don't need to know which steps are slow or fast. That was only for the rate determining step approximations. Rate determining step approximation. So, all right, so from elementary reactions 2 and 3 that I already showed like 3 times here, we find the rate law, or well, the concentration for that. We're adding it in reaction 2 and subtracting it in reaction 3. So the derivative of the concentration, the ONBR, with respect to time, is equal to positive K2 times the concentration at H2NO2 plus times the concentration of the bromide minus K3 times the concentration at ONBR over the concentration of this C6H5NH2. And since we're applying the steady state approximation, this is an intermediate, so its concentration is going to be constant over time, so the derivative is going to be equal to 0. So just using this part, not worry about that now, then we're going to solve for the ONBR, since that's the intermediate that we're trying to substitute out for. So this gives us that the concentration, the ONBR, is just equal to the rate constant of K2 times the concentration of H2NO2 plus times the concentration of Br minus, divided by the rate constant K3 times the C6H5NH2. Now we're going to substitute this back into equation 1 that was on a previous slide, and that's going to give us the R is equal to K3 times K2 over K3 times H2NO2 plus times the concentration of Br minus times the concentration of this aniline divided by the concentration of aniline. These two K3s, they'll cancel out, and the concentration of the aniline will cancel out. So this just leaves us then R is equal to K2 times the concentration of H2NO2 plus times Br, concentration of Br minus. We're going to call this equation 2. So this is another rate law just like we had before, but it still suffers from the same obvious problem. It's got an intermediate in it. The intermediate this time is a different one though, the H2NO2 plus. And again, we need to substitute this out so we have a rate law that we're actually allowed to use. So what we're going to do is we're going to apply the steady state approximation to separate time. We're going to say, okay, the concentration of this is constant over time. And now give us a formula to substitute that out. All right, continuing on this approximation, steady state approximation. So for the second intermediate that we're setting equal to 0, it's in 2 steps, and one of them is in equilibrium. So the derivative of the concentrations H2NO2 plus with respect to time is equal to positive K1 times the concentration H plus times the concentration HNO2 minus that K minus 1 rate constant, that's the concentration of H2NO2 plus, minus this rate constant K2 times the concentration at H2NO2 plus times the concentration of Br minus, and we're setting that equal to 0 because we're saying as an intermediate this concentration will be constant over time. Then just taking this side and solving for the concentration of our intermediate, we get the concentration of H2NO2 plus is equal to K1 times H plus times HNO2 divided by K minus 1 plus K2 times Br minus. Now we're going to take that whole thing and substitute back into equation 2. So what we have is the rate is equal to K2 times K1 times the concentration of H plus times the concentration of HNO2 times Br minus divided by this rate constant K minus 1 plus K2 times the concentration of Br minus. Now, this is our rate law. We're done because there are no intermediates in our formula. So as you can see, it's more complicated than the one we got from the rate determining step method. But sometimes you can simplify this. For example, what if these rate constants, the units don't work out here, but I'm not going to simplify. So like K minus 1 greater than K2, those all have different units, so actually it should be K minus 1 is greater than K2 times the concentration of this. But anyway, so if that is the case then, this bottom part, you can just get rid of this and simplify it, just approximate it to K minus 1. So then you just have this, rate is equal to K2 times K1 over K minus 1 times H plus times HNO2 times Br minus. You combine these into one constant K. K is equal to K2 times K1 over K minus 1. So you get R is equal to K times the concentration H plus, concentration HNO2 times the concentration of the bromide. So this will give you a third order reaction. Remember up here you can't say the order because it doesn't fit the simple format that we have. On the other hand, if this K2 is greater than K1, or should I say K2 times this concentration is greater than K1, so the units are appropriate, then what happens, let's see, this disappears, you have this. and the K2s are going to cancel out, and the bromides are going to cancel out, concentration of the bromide. So we get R is equal to K1 times K2 over K2, times H plus times HNO2 times the bromide over K2 times the bromide. So you notice these K2s, well, this one pair of yeah, you get the idea. Oh, did I screw something up? I think I did miss something. But anyway, so we get R is equal to K1 times concentration H plus times HNO2. That's supposed to be a 2 here. Yes. So notice now, it looks like a second order equation. This is almost the exact same equation, it's just what are the rate constants. That's again why you have to experimentally determine this stuff. Find the rate constants so you can see, is it going to fit this or is it going to fit that? Okay, physical chemistry, we're doing chapter 17. We skipped section 7 in case you didn't notice. We're doing section 8 now. This is where we're going to talk about the temperature dependence of rate constants. Now we mentioned before that the rate constants, they are slightly dependent on pressure, but they are extremely dependent on temperature. In fact, the rate constants are exponentially dependent on temperature. Now Arrhenius is the one who derived this equation for temperature dependency. And this is all it is. The rate constant is equal to A times e to the minus EA over RT. Now remember, K is this rate constant that we're interested in talking about. T is the absolute temperature in kelvins, obviously. R is just the gas constant, 8.314 joules per whole Kelvin. And then the EA, that's the activation energy for a specific reaction. Now, EA over RT obviously is dimensionless. It has no units because we've got it up in the exponent to this natural number, 2.718. Now this A here, this is called the pre-exponential factor. It's obviously got the same units as K since e to whatever is going to have no units. Now we've shown a lot of times how if you have multiple constants, you multiply them or divide them or whatever, and you combine them to make a new constant. So A here is a constant that's combined from several others. For one thing, it's from the collision frequency of the molecules back in chapter 15. So this is obviously going to be material specific. And then likewise, the size of the molecules. Obviously, bigger molecules, they're going to, take up the collisions. And then orientation. You know, not all molecules are perfect spheres. You know, if you have a protein, you've only got that tiny little acid pocket. So you need your, you need your substances to go into that acid pocket to come together or break apart. So this orientation is going to, we also call that a probability factor. It's just a, when two molecules collide, what's the probability that they're going to do anything? Okay, continuing on what we were talking about, the Arrhenius equation. So we already said A is the pre-exponential factor, but it's also called the frequency factor. I want to throw that in there. So A is a measure of collision rate irrespective of the molecule's energy. Now remember, EA is the activation energy. It's the minimum energy that reactant molecules must have in order to form products. We could call that a filtering factor. Now, solving the Arrhenius equation, basically taking the natural log of both sides like this, solving for natural log of K. We get natural log of K is equal to natural log of A minus EA over RT. So now what we have is a straight line, y equals b minus mx, basically. So we're graphing natural log of K against 1 over t. Notice it has a negative slope here. The slope is minus EA over R. So if you do an experiment, you find the natural log of K at different temperatures and you graph it, you'll get a straight line. And from the slope, you can find the activation energy of your reaction. Might be kind of handy if you want to know what the activation energy is. So what this should tell you then, if the activation energy goes to infinity, then the rate constant will go to 0. And like vice versa will be true. If the activation energy gets really small, then K will get really big. So you can rewrite the Arrhenius equation like this. K is equal to A over E to the EA over RT. Since remember, normally it was K is equal to A times E to the minus EA over RT. Now, EA is normally about 0 to 80 kilocalories per mole, or 330 kilojoules per mole. But free radical reactions, they'll have an activation energy roughly 0. We'll talk more about free radical reactions in a bit. Okay, we're continuing to talk about how the rate constant K varies with temperature, and we show that it's exponential. So here we just have K versus T, and yep, up it goes, exponential. So, and we also said for free radicals, the activation energy is 0. Like here's a CH3 radical and a CH3 radical, and that's going to go one way to just C2H6. And the activation energy is 0, and that's actually what makes them dangerous. One possible example is when you cook red meat, if it's got nitrite in it, they can put red nitrite in it to keep it looking red because nobody wants gross looking meat. But then the nitrites, it will turn into free radicals when you heat them up. Okay, so now let's talk about one reaction, but we're going to do the same experiment at 2 different temperatures. Temperature 1, temperature 2. So for temperature 1, we're going to say, okay, the rate constant 1 is equal to A times e to the minus EA over RT1. And this will be equation 1. And then likewise, we're going to repeat the experiment at temperature 2. So we have rate constant 2 is equal to A times e to the minus EA over RT2. Now R, of course, is a constant for real. EA is not going to change for the reaction. It's not dependent on temperature for our purposes. And then officially, we're calling A constant too. So what we're going to do, we're going to say K1 and K2, oh yeah, I already said K1 and K2 are the same reaction, just different temperature. We're going to divide these 2 equations to see what happens. Alright, continuing to talk about the rate or temperature dependence of rate constants. So we divided those 2 equations. So we get rate constant 2 over 1 is equal to e to the minus EA over RT2 over e to the minus EA over RT1. Just using your rules of exponents, algebra, etc., that gives us e to the positive EA over RT1 times e to the minus EA over RT2. And again, just combining the exponents, we get e to the EA over R times 1 over T1 minus 1 over T2. Then just take the natural log of both sides. We've got the natural log of rate constant 2 divided by rate constant 1 equals EA over R times T2 minus T1 over T1 T2. We just did that to change the format, no big deal. Alright, so now let's graph it and see what happens. So we're going to graph this ratio, the rate constant at the higher temperature divided by the rate constant at the lower temperature against the activation energy. And as you can see, it's exponential. At lower activation energies, it's not going to be as much difference between the K at higher temperature versus the lower temperature. Here we're using T2 is 310 Kelvin and T1 is 300 kelvins. So there's only a few percent difference in temperature. But as you can see, at higher activation energies for a reaction, then the ratio of the rate constant at higher temperature versus the lower temperature is much bigger. So this should tell you that as activation energy with a reaction, the difference temperature makes in a reaction is very large. Now remember we said for an elementary reaction or a single step that the forward rate constant divided by the reverse rate constant is equal to the molar concentration reaction equilibrium constant. So just take the natural log of both sides and do some arithmetic there. We get the natural log of the forward rate constant minus the natural log of the reverse rate constant is equal to the natural log of the equilibrium constant. And then we're going to just divide by the differential of capital T. Remember, lowercase t is time, capital T is temperature. You should know that, we've been doing temperature up here. So then we have the derivative of the natural log of the forward rate constant with respect to temperature, minus the derivative of the natural log of the reverse rate constant with respect to temperature, and that's equal to the derivative of the natural log of the equilibrium constant with respect to temperature. We're going to call this equation 3 because we're going to come back to it later. Okay, so also from the Arrhenius equation, we have the natural log of K, that's rate constant, equals the natural log of A minus EA, activation energy, over RT. So we have the derivative of natural log of k with respect to temperature is equal to the derivative of natural log of A with respect to temperature minus the derivative with respect to temperature of EA over RT, and that's going to be equal to EA over RT squared. So equation 4 is just the derivative of the natural log of the rate constant K with respect to temperature is equal to EA over RT squared. Now, remember we said before, if EA is roughly equal to 0, the activation energy is roughly equal to 0, then the derivative of the natural log of K with respect to temperature is going to be equal to 0. This is the rare case, like free radical reactions. Now, in that case, then, the rate constant doesn't depend on temperature. That should have been obvious from the graph anyway. So now we're going to substitute equation 4 in equation 3. We have the derivative of the natural log of the forward rate constant with respect to temperature minus the derivative of the natural log of the reverse rate constant with respect to temperature is equal to the derivative of the natural log of the equilibrium constant with respect to temperature. Now we also know that the activation energy of the forward reaction divided by RT squared minus the activation energy of the reverse reaction divided by RT squared is equal to the change in internal energy, does not remember standard state, divided by RT squared. We're just going to go ahead and divide by RT, or cancel out all the RT squares. Alright, continuing on physical chemistry, chapter 17, section 8. We're still talking about how the equilibrium constants change with temperature. So we also have the derivative of the natural log of the equilibrium Kp naught with respect to temperature is equal to delta H naught over RT squared. Except remember, we have Kc, not Kp naught, because, well, Kp naught would be like, we don't have delta H. So this is a reaction, oh yeah, before I do that. So the energy of activation for the forward reaction minus the energy of activation for the reverse reaction is the change in actual energy, internal energy, at constant, steady state, standard state. So here we have the energy of activation, or just energy versus reaction coordinate. So we're doing an endothermic reaction because we're starting out at higher temperature here. So this is our reaction coordinate, the reaction pathway. Over here we have our reactants, over here we have our products. So anyway, so down here we have lower energy, up here we have higher energy, that's why it's endothermic. So the distance from the bottom here to the top here, the vertical distance, that's the forward energy of activation. And the vertical distance from the products up here, that's our reverse energy of activation. And this difference in height here, this is our change in the internal energy at the standard state. And again, remember, this is delta U, not delta H. So make sure you pay attention to which equilibrium constants you have, which apply where, etc. So remember we have K is, this is the Arrhenius equation. K is equal to A times E to the minus EA over RT. And remember, this is the activation energy for the overall reaction. So, for example, let's say we have a composite reaction where we have equilibrium and then a one-way reaction. So our K overall is just going to be this K1 times K2, the forward reaction rate constants, divided by K to the minus 1, because that's the reverse rate constant. That's going to be equal to A times E to the minus EA over RT, and again, that's the EA for the overall reaction. So it's going to be EA for the forward reaction minus EA of the reverse reaction plus EA of the forward second reaction.